Hello and welcome to another chemistry lecture by Dr. Armand. Today will be a shorter lecture than usual. We'll be talking about the electron configuration of ions, namely talking about the electron configuration of S block cations, D block cations, P block cations, and P block anions. How do we determine the electron configuration of those ions? And also we'll talk about the difference between paramagnetic and diamagnetic species and go through several examples illustrating these concepts. So sit back, relax, let the chemistry take you over. Like I said, this is the second installment of the lecture on electron configuration. The last lecture was about how to write electron configuration of elements. Today we're going to expand that and talk about ions. And there are four main groups of ions we're going to talk about today. The first one is the main group S block metals. Those are going to be your group 1 and group 2 metals. So it's going to be group 1 and group 2 cations. And so for the group 1, group 2 cations, you always remove from the highest field s orbital because those are always the last filled orbitals for those types of species. So for example, if we were looking at sodium, sodium is argon, argon 3s1. If we want to look at sodium plus, we remove the electron from the highest filled orbital, and that's going to be the 3s. So for sodium plus, it's just going to be argon. Oh, excuse me, I got that backwards. It's neon. My bad, my bad. Just double checking here. And so with S block metals, their cations are going to have the same electron configuration as the previous noble gas. So that's with the S block metals. We always remove from the highest orbital, which will be the last filled S orbital is the highest orbital. Now we're moving to main block P block main group P block metals, and these are going to be like your group 13, 14, 15 metal cations. From there, we remove from the highest filled P, then S, highest filled S orbital. Now for P block, you never remove from D orbital. P block cations are never removed from the D orbital. Remember that, that's very important. So for example, and again, it's not just limited to 15, it can be group 16, like some of the heavier group 16s like tellurium may be positive charge, etc. So, 13, 14, 15, 16 are common P block cations. So for example, if we have, say, phosphorus, phosphorus is argon 3s2 3p3. Not argon. Again, I get confused argon and neon. Now, if we want to do phosphorus 3 plus, again, we got to remove from the highest orbital first. And again, if you're on the same energy level, the higher the L value, the higher energy orbital it is. So we move from the 3p first. So it becomes neon 3s2. That's the electron configuration of p phosphorus 3 plus. Again, you never remove from the d orbital for p block cations. Now with transition metals, you remove from the s orbital first, and then the d orbital. And this is because once you start filling the s and d orbital, the s orbital becomes higher in energy than the d orbital. So for transition metal cations, you remove from the highest filled s, and then the highest filled d orbital. And again, the reason is because once the electrons occupy the orbital, then the s and p switch in energy. So then the 4s is higher in energy than the 3d. And the same goes for 5s and 4d. Before you fill them with electrons, the s is lower than the d. But once you fill them with electrons, they switch, and the s becomes higher in energy than the d. So for example, if we have iron is argon 4s2, 3d, I believe it's 3d6. So iron 3 plus again is going to be argon. We remove from the s orbital first, that removes 2, and then we remove 1 from the d, we get 3d5. The most common mistake is that students forget that the s orbital comes first when you're removing electrons, followed by the d orbital. That's probably the most difficult one out of all of these groups, is the d block cations. Now for nonmetals, these are going to be your p block nonmetals, which are the only nonmetals basically on the periodic table. You always add to the highest filled p orbital. And the p block anions have the same configuration as the noble gas that comes after it. So for example, we have oxygen. Oxygen is helium 2s2 2p4. And then we have the oxide. So now we're going to add 2 electrons to the p orbital, so we get neon. So again, with the anions, it's always going to have the configuration of the noble gas that comes after the element in the p block. So oxygen, you go oxide, it's going to have the same electron configuration as neon. And again, we're going to go over some examples as well. One last thing we want to talk about before we do some examples is something called the magnetic properties of transition metal ions. So there are two types of magnetic properties. You have paramagnetic and diamagnetic. And so the main difference between them is paramagnetic species have an unpaired electrons and they're affected by a magnetic field. So they're attracted to a magnetic field. So anything with an unpair of electrons is paramagnetic. So for example, if we look at oxygen, oxygen is helium 2s2 2p4. If we were to draw the orbital diagram of oxygen, two s and 2p. Now if we start filling these electrons, you see oxygen has two lone electrons. So oxygen is paramagnetic, however oxide is diamagnetic because oxide does not have any single lone electrons. So species with lone electrons or unpaired electrons are paramagnetic. Now diamagnetic are species that have all paired electrons, and certain groups of elements are diamagnetic. And those groups are group 2, so the alkaline earth metals are diamagnetic. Group 12 or 2b, so that's the zinc, cadmium, mercury group. And group 18, the noble gases. So these three groups, their elements are always diamagnetic. So any other element that's not one of these three groups is going to be paramagnetic. So you need to remember that. So elements, we're just talking about elements, not ions. Elements, only group 2, group 12, or 2b, and group 18 are diamagnetic. All other elements are paramagnetic. Now for ions, some common trends here. Ions, main, or I should say S block cations, P block anions are always diamagnetic. The other ones you have to double check. Others you have to check. But if it's a S block cation or a P block anion, they're always diamagnetic. Most P block cations are diamagnetic. Transition metals, though, it depends. So here we have silver. Remember, silver is an exception, 5s1 4d10. So silver is paramagnetic because it has a lone electron in it. Tin is paramagnetic, and so is tin 2 plus. Because remember, with D block transition metals, you take from the S first. So tin and tin 2 plus are paramagnetic. However, tin 4 plus would be diamagnetic. Also, copper is paramagnetic, but copper plus is diamagnetic. Copper plus has no lone electrons. Zinc is diamagnetic, and zinc 2 plus is also diamagnetic because again they have no lone electrons. So copper plus, zinc 2 plus are all diamagnetic. So again, what you're looking for is lone electrons. If a species has lone electrons, it's paramagnetic. If it doesn't, it's referred to as diamagnetic. And this is important because when you start looking at things like NMR, nuclear magnetic resonance, those species that are paramagnetic cause issues with NMR. They affect the magnetic field. So now let's look at some examples. So here we want to know what's the shorthand configuration of bismuth 3 plus. So bismuth is located here. The preceding noble gas to bismuth is xenon. So that's where we're going to start off with in our shorthand electron configuration. First, we're going to write the shorthand for bismuth. So it's xenon. And then we start on the 6th row. So the 6th row, we have the 6s shown here. And it's completely filled, so the 6s. Oops. Next, we have the 4f, which is shown here, and it's also completely filled. Then we have the 5d, and it is completely filled. Because again, the d orbital is 1 minus the period. And then lastly, we have 3p electrons. And since it's on the 6th row, this is 6p. So now we can write the electron configuration of bismuth, which is 6s2, 4f14, 5d10, 6p3. Now we want to write the electron configuration for bismuth 3 plus. So we always remove from the highest orbital first. So the highest orbital here is going to be the 6p because p is higher in energy than s. So we're going to have xenon 6s2, 4f14, 5d10. And so what you should note here is that bismuth is paramagnetic. However, bismuth 3 plus is diamagnetic because there's no lone electrons because we have all completely filled orbitals. So you can change the magnetic properties of an element by changing it from an element to an ion. Next, we want to look at the electron configuration of selenium. So again, selenium is located on the 4th row. And I'm showing the long way to do this, but if you know a shorter way, more than welcome to do shorter ways, but I'm just showing you every step. And so the preceding noble gas to selenium is argon. And so we know that selenium has argon as the shorthand, so we have selenium, argon, and then we're starting on the 4th row. So we know we have a completely filled 4s orbital. This is 4s. It's completely filled. And then we have a completely filled d orbital. Since we're on the 4th row, the d orbital is 3d, because it's always 1 minus the row tells you the d orbital that you have. And this is completely filled as well. So this is 3d. Then we have some elements, or excuse me, electrons after that in the p orbital. We have 4 p electrons. And since we're on the 4th row, this is the 4p orbital. So now we can write the electron configuration of selenium. It's 4s2, 3d, 10, 4p, 4. Now if we want to write the electron configuration of selenide, we add 2 electrons to the last orbital, which is the 4p orbital. So 4s2, 3d10, 4p6, which is the electron configuration of krypton. So the answer would be krypton. So the electron configuration of selenide is krypton. Next we have molybdenum 3+. So again, molybdenum is located on the 5th row. The preceding noble gas is krypton. And we have a completely filled s orbital, so that's going to be 5s. And then we have a partially filled 4d orbital. And the reason it's 4d is because it's 1 minus the row it's on. We write the electron configuration of molybdenum, krypton, 5s2, 4d4. But wait a second, you're right, this is an exception. So it's actually molybdenum is krypton, 5s1, 4d5. Remember, molybdenum is one of those exceptions we talked about in the last lecture. So now we want to make molybdenum 3+. So what does that mean? We're going to remove from the highest filled energy level, which is the 5s1. So we remove 1 electron from the 5s orbital and 2 electrons from the 4d. So it'd be krypton 4d3. And both of these are paramagnetic species. So we want to write the shorthand electron configuration of cesium. So cesium is located on the 6th row. So that means the last filled orbital is going to be 6s. And the preceding noble gas is xenon. So to write this electron configuration for cesium would be xenon 6s1. Now to write the electron configuration of cesium plus, we remove from the highest orbital, which is the 6s, so we just get xenon. So cesium is paramagnetic. However, cesium plus is diamagnetic. So you can change its magnetic properties. We already did shorthand electron configuration. Okay. Now we want to determine how many lone electrons does antimony 3 plus have. So let's write the electron configuration of antimony 3 plus. So antimony is located here, it's Sb. It's on the 5th row. And it's antimony 3 plus, so we're going to get rid of 3 electrons. So 1, 2, 3. So what do we have left? Well, again, the preceding noble gas is krypton. So we know antimony 3 plus. We start with krypton. And then we know that we have a completely filled s orbital, which is the 5s, because there's 2 right there. So that's 5s. And then we have a completely filled d orbital. Since we're on the 5th row, 1 minus the row tells us the d orbital, which is 4d. Again, we don't count the 5p because we removed those electrons. We don't count those that we removed. This is 4d. So the electron configuration would be krypton 5s2 4d10. And since it has a completely filled s and d orbital, it has 0 lone electrons. So it is diamagnetic. Again, it's 0 lone electrons because you have completely filled s and d orbitals. Next, we have silicon 2 plus. So again, where is silicon? It's located on the 3rd row here, and since it's 2 plus, we're going to remove 2 electrons. So we go 1, 2. So we're going to move those 2 electrons. The preceding noble gas is neon. After neon, we have a filled s orbital. And since it's on the 3rd row, this is 3s. And so for silicon 2 plus, it would be neon 3s2. And since it has a completely filled s orbital, it has 0 lone electrons. It is diamagnetic. Paramagnetic. Now we get to manganese 3 plus. So manganese is different. It's a transition metal. So it's located right here. The preceding noble gas is argon. Now we know manganese 3 plus is going to have argon in the electron configuration. We'll go ahead and put that. Now we see here that it's manganese 3 plus, and when you're doing electron configuration of transition metals, where do you remove from first? That's correct. We remove from the highest S, then the D. So let's remove from the highest filled S orbital. That's going to be right here. So we're going to go 1, 2, 3. So we remove 3 electrons. So those are gone. So the 5s orbital, or excuse me, the 4s orbital is completely empty. And then we remove 1d electron. So what we have left is this right here. And that would give us, since it's on the 4th row, it's a 3d, and we have 4 3d electrons. So this would be 3d 4. Now if we look at the orbital diagram of this, so 3d, we got 4d electrons, so we go 1, we got to follow Hund's rule, 2, 3, 4. So that tells us we have 4 lone electrons, which is paramagnetic. So again, for transition metals, always remove from the highest S, then the highest D orbital. Next we have molybdenum 4 plus. So molybdenum 4 plus, so let's show you where molybdenum is. It's located right here. Now molybdenum is an exception, so what I'm going to do first is I'm going to write the electron configuration of molybdenum, and then we'll determine the number of lone electrons in molybdenum 4 plus. So molybdenum, the previous noble gas, is krypton. After krypton, we have a completely filled S orbital. So this is 5s, because the row number tells you the S orbital. And then we have 4 4d electrons. Sorry about that. Because the way we know it's 4d is because it's on the 5th row, so it has to be the 4d orbital. So for molybdenum, krypton 5s2 4d4. However, this is an exception. So it needs to be written as krypton 5s1 4d4. 5. So that's the correct electron configuration of molybdenum. Now do molybdenum 4 plus. Again, we remove from the s orbital first, then the d. So 1 electron from the s orbital, 3 from the d orbital, and we have krypton 4d2. And since it's 4d2, 1, 2, 3. 4d2, we follow Hund's rule. We have 1, 2. So there's going to be 2 lone electrons. Paramagnetic. So the last question, we just want to kind of recap. So we want to know which of the following species are paramagnetic. Let's first look at the elements. So the only element we have on this answer choice is aluminum. And remember, for elements, only group 2, 12, and 18 are diamagnetic. So is aluminum group 2, 12, or 18? No. So aluminum is a paramagnetic compound. Next, we want to look at the ions. And so from what I said earlier, for ions, what we know for sure is S block cations and P block anions are diamagnetic. So do we have any S block cations or P block anions? Well, yes, A is an S block cation, so A won't be a choice. Do we have any P block anions? Yes, sulfide, so that won't be a choice. So what we're left with is iron, copper, lead, and chromium. So for iron, 2 plus, its electron configuration is argon 3d6. So does 3d6 have lone electrons? Let's look. So if we add 6 electrons, we got 1, 2, 3, 4, 5, 6. So yes, it does. So iron 2 plus is paramagnetic. Now we go to copper 2 plus. And by the way, if you don't have 10 electrons in a d orbital, then it's going to have lone electrons. So now we look at copper 2 plus, and copper 2 plus is an exception. We know that copper is argon 4s1 3d 10, because remember it's an exception. You have a half filled S and a completely filled D. Now copper 2 plus, we remove from the S first, then the D, we get argon 3d 9. So since the d orbital is not completely filled, it's going to have lone electrons. It's paramagnetic. Next we go to lead 4 plus. So we know lead is going to be xenon 6s2 4f14 5d10 6p2. And so lead 2 plus, we remove from the highest orbital first, which is 6p. We remove 2 electrons. The next highest is 6s. So lead 2 plus is xenon 4f14 5d10. So completely filled f and d orbitals, no lone electrons. So it's going to be diamagnetic. So we can cross it out. Lastly, we have chromium 4 plus. So again, remember chromium is an exception. So chromium is argon 4s1 3d5. Now we want to get chromium 4 plus. We remove from the, that's right, the s orbital first, and then the d. So we get argon 3d2. Is that right? Yes. And since it's an unfilled d orbital, it has lone electrons. So it would be paramagnetic. So that's what you're looking for. Paramagnetic has lone electrons. Diamagnetic has all paired electrons. And for d orbitals, if your d orbital has less than 10 electrons, it's going to have lone electrons in it. So that concludes today's lecture on electron configuration of ions and paramagnetic diamagnetic species. The next installment of these topics will be on periodic trends. So for example, periodic trends are things that increase or decrease as you move across the periodic table. And these will include things like atomic radii, ionic radii, ionization energy, electron affinity, isoelectronic species, valence electrons. So those are all different types of periodic properties that we will be discussing. So until next time, Dr. Armand is signing off.